Lesson 2, relations. In math, the word relation simply means to some kind of a rule that relates one thing to another. The more obvious ones are equations, but there are lots of real-life relations. So much of mathematics, it says, involves the search for patterns and relationships in sets of data. Many real-life applications of mathematics investigate the relationship between two quantities. For example, the value of a computer is related to its age. As your computer gets older, what happens to its overall value? Gets lower. This would be an example of where one gets bigger, one gets smaller. Age gets bigger, value gets smaller. The price of a watermelon is related to its weight. As a watermelon gets heavier, what happens to its price? Gets smaller? Who said? Someone, you need to go shopping. Yeah, I think it goes up, right? This is an example of where one goes up, the other goes up. The time taken for a person to walk to school is related to the distance to be walked. The further you live, the more time it takes you. Pardon me? Unless you have a car. But even, okay, further you live, the more time it takes you to drive. But that would be looking at two different types of relations. Yeah, that's right. And in fact, then if you were to graph those, you could find things like, where's the break-even point? I'm willing to bet if someone lives within a half a block here, they can get to school faster than anybody in a car, no matter what, in terms of the time to start up the car and back out of the... So you could actually do some extrapolation that way. In mathematics, so a comparison between two sets of elements is called a relation. A rule that relates one thing to another, a comparison. List one more example of a relation. Let's make something up. How about this is for Anthony. The number of points a team averages is related to how many games it can win. Now, this is a bit of a changing one. You play basketball. If your team averages more points, is it more likely that it will win games? Yeah. But have you been in some games where you scored a lot of points and lost? Yeah, this is not a blatant one-to-one guaranteed relation, unlike the previous ones. The previous ones, although that first one, the value of a computer is related to its age, that's true for a while, but then eventually the computer starts to be worth more. Why? Now it's a collectible, right? It's an antique. Okay, so that one also does change. We talked about dependent and independent variables. We said which one affects the other. The independent affects the dependent. For example, I think the age is the independent variable in the first one. I think the value of the computer is the dependent. How much a computer is worth depends on its age, not the other way around. In the example that I made up, I think the number of wins is the dependent, and it depends on how many points you score. Certainly, if you average 10 points a game as a basketball team, you're not going to be winning too many games unless you have the most phenomenal defense I've ever seen. However, if you average 105 points a game, like the Lakers, you still might not be winning too many games if your defense really sucks. So there's other factors at play as well. In this unit, we're going to look at 7 ways in which we can represent relations. Some of these ways are already familiar to us. Words, like I've just done. A table of values. Oh, we did those last day. A set of ordered pairs. Oh, Jordan, that's when we took that table of values and just said, let the first thing be an X, let the second thing be a Y. A mapping or an arrow diagram, that might be a new one, but it's a pretty intuitive one. I think you'll figure it out. An equation, y equals 3x plus 2. The number of stars equals 2 times the number of dots, or the number of figures plus 2, whatever the equation was. And a graph. And the last one is function notation. In fact, function notation is what we're going to spend a lot of time on. We're going to use the relation below as an example. So here's the relation in English, in words. The cost, I don't want to write the word cost out all the time. What would be a good letter to use as an abbreviation for the word cost? Capital C, we'll include that. And we should mention the units. Cost is going to be measured in the number of cents per kilometer, the number of pennies per kilometer. Of driving a car is related to the speed. What would be a good letter to use for speed? S. And we'll measure our speed in kilometers per hour at which it is driven. We're going to use this relation to introduce some ideas. Our task is to represent this in some form. You ready? Here we go. So this illustrates a relationship between two variables. What are my two variables? C and S, X and Y, J and K, whatever. I use X and Y if it's a generic graph. Otherwise, I'll try and use the first letter of whatever we're talking about, unless they both have the same first letter, like toothpicks and triangles a couple of days ago. Then I'll use different letters. In the statement of the relation, how much it costs depends on how fast you're going. Did you hear me say the word depends? Cost is the dependent variable. S is the independent variable. The independent variable, is often called the input. How can I remember that the input is usually the independent variable? I got nothing. Maybe you'll come up with something. Yes. And the output is the dependent variable. Before we can do much more with this, Amy, I've given you the rule in words. We need some actual data. Okay? So I've made up some data on the next page, but before you turn the page, for what it's worth, and we're going to spend a lot of time talking about this, but I want to introduce the words right now. The fancy name for the input values, we call that the domain. And the fancy name for the output values, we call that the range. We're going to spend a lot of time talking about the domain and the range of a relation of a function. Turn the page. So let's suppose you were analyzing a car and you had some kind of a machine hooked up to the car's motor that could measure how much it was costing per kilometer at a specific speed. You wouldn't collect every single speed. You wouldn't try 1 kilometer an hour, 2 kilometers an hour, 3 kilometers. You'd probably try every so often. You'd probably say 10 kilometers per hour. I'll try 20 kilometers per hour. I'll try 30. You'd probably go up by tens. And so here we have it. We've chosen as our input values, we started out with 20 kilometers an hour, and we've measured the cost it costs us per kilometer every 10 kilometers increase, per hour increase. So here's how we can represent that. Here's our table of values. Here's our ordered pairs, 20, 10, 30, 9.1, 40, 8.4, ordered pairs. As a graph, now if we did this as a graph, we would put the independent value on the x-axis and the dependent value on the y-axis. So my x-axis would be 10, 20, 30, 40. I'd probably label every other one so it wasn't so cluttered. My y-axis, now, because my first value, my lowest value seems to be this 7.5 right here, I probably wouldn't want to include all the way down to 0 because that's a waste of graph paper. So Amber, when you when you cut off part of the graph paper, you show that by putting a little jagged line like that. That tells people, I chopped off the graph paper because I just didn't want to waste paper. Ooh, that graph makes a shape. Does anybody remember what I called that shape? We've seen this horseshoe shape before. Ooh, what? Parabola. It's a parabola. This is another place where a parabola appears. Parabolas appear all over the place, which is why you look at them so much in Math 11 next year. Show you one place where they appear right now, but I got to pause the video. Here's a mapping diagram. What does a mapping diagram look like? Ashley, you list all of your independent variables in a great big oval. You list all of your dependent variables in another oval. and then you just draw arrows connecting which ones go together. I don't like them that much. They're useful in some ways, but they're very cluttered. They're very cluttered. The only way that they're useful is you can easily tell how many different independent variables gave you the same answer. How many arrows point to 10? I guess twice I got the answer of 10 when I was testing. Twice I got the answer of 9.1 when I was testing. That's about the only place they have an advantage. Meh. Next page. We've only chosen some of the possible input values. However, it's obvious that an output value could have been determined for any input value. I think this graph, although we initially plotted it as a discrete, I think we could connect the dots, because can you travel 26 kilometers per hour? Can you travel 26.1 kilometers per hour? Yeah. Can you travel 26.11? I think from the data, we graphed it, but we would certainly, I think, choose to connect it. And as a matter of fact, I can even tell you the equation. The equation is this thing. How the heck did they find that? They cheated. They used a computer. There is a way that you can type in points into a computer and have it generate the equation. But I'll convince you that it works. So here's my equation. One of the points on this graph was we plugged in a 30. If I put in a 30 right there, if I go 0.001 times 30 squared minus 0.14 times 30 plus 12.4, I get 9.1. Is that what the table of values said went with 30 on the previous page? Yeah. This is a complicated equation, probably not one that you would have been able to get in your head. They used a computer, but it is the right equation. Now, this graph is continuous, but my domain is not infinite. For example, would it make sense to graph a speed of 5,000 kilometers per hour? Can a car go 5,000 kilometers per hour? Brody? No. Your domain is probably between 0, because a car can stop, and 200 maybe is about the fastest a car can go. That would be the list of values that would be acceptable. So the graph and the equation are given below. Note that the equation is only valid for certain input values, which make up the domain. For example, the equation would not be valid for a speed of 5,000. That'd be silly. Lots of terminology, I know. Turn the page. The independent variable represents the inputs. That's the first variable, the x-coordinate. The dependent variable are the outputs. When I give you an ordered pair, the first coordinate is the independent variable. The second coordinate is the dependent variable. In a table of values, almost always the first column or the first thing is the independent. It's either given to the left or on top. In a mapping diagram, arrows go from the independent to the dependent. On a graph, the independent variable, this you need to know, is on the x-axis. The dependent variable is on the y-axis. Last thing, if we can, if it's not too much work, Sam, we will try and isolate the dependent variable to the left-hand side of an equation. Sometimes you can't. Usually you can. So if we summarize all this, here's an equation, y equals 3x minus 5. There's my independent variable. We got the dependent variable by itself. These are my outputs. These are my inputs. If I give you the point, the x-coordinate comes first, the y-coordinate comes second. Let's do something. Next page. says the diagrams below show relations expressed in different ways. In each case, the first thing it wants us to do is to state the independent variable. So we can do that. What's the independent variable in part A? In this mapping diagram, what's the independent variable? P. What's the independent variable in this table of values? V. What's the independent variable in this particular ordered pair? I think capital B. Yes? What's the second thing it wants me to do? Q, A, little c. 3 says, list the inputs. What are the inputs for A? 5, 8, and 11. What are the inputs for B? 4, 10, and 25. What are the inputs for C? 3, 4, 5, and 6. I'm not going to write these down because we're running out of room. Then list the outputs, the Y values, 10 and 16, 15, 12, and 15, 7, 11, 15, and 19. The diagrams below show relations expressed in different ways. In each case, state the independent variable, state the dependent variable. Okay. A. Which one of those is the independent variable? Let's see. We said that the independent variable, we said the dependent variable is usually by itself. Does it care to revise your answer? What? Pi is not a variable. Pi is a number. Which one? R? I went to go see a pirate movie the other day, but I couldn't get in because it was rated R. No? Okay. The dependent is C. By the way, does anybody recognize that equation? C equals 2 pi R. What is it? An equation, the equation of? It's the circumference of a circle. If you want to find out how far it is around a circle, measure the radius and times it by 2 pi. Here we have, and I apologize, there's kind of a glitchy thing that appeared and I don't know how to get rid of it, but anyways, which of these in this second one is the independent variable? Too slow. Let's go back. Let's see. The independent variable, which is the first coordinate, is traditionally put on which axis? X-axis, the horizontal axis. So which is the independent variable? Time. Which is the dependent variable? Oh yeah, that makes sense. How tall you are depends on how old you are. How old you are does not depend on how tall you are. C. The amount of sap, S, obtained from a tree is dependent on the time T a container is left attached. So which of these do you think is the independent? Well, which is the dependent one? S. So which is the independent one? So now we're going to shift gears a little bit. We're going to consider relations defined by an equation. We're going to sketch a graph. Turn the page. No, I don't. Ready? Here's our relation, y equals 2x minus 5. It says complete the first 5 rows of the following table of values. So what we're going to do is we're going to input for that x each of these. You can either do these in your head or with a calculator. I'll do it on a calculator just so you can see what we're doing. So the equation is as follows. 2 times x. What's the first x value they want me to use? Minus 5. When I input a negative 2, what's the output value? As an ordered pair, negative 2, comma, negative 9 is on that graph, is part of that relation. In fact, I'm going to plot that right now. Negative 2, negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, by the way, do you guys know what this graph looks like? How can you tell that that's going to be a straight line? How do you know it's not a curve? No crazy weird thing. No squares, no square roots. I'm expecting a line, which means if something doesn't line up, I know I've made a mistake. Yes? What's the next input value they want me to try, Kira? Okay, let's see if we can do this in our heads. Imagine a little negative 1 right there. 2 times negative 1. Minus 5. Yep. So what you're really saying is negative 1, comma, negative 7 is a point on my graph. Let's put that on there. It looks like a line, but Garrett, 2 points isn't enough to convince me. I could be wrong, and I would have no way of knowing. I always do at least 3 to see if they line up. Garrett, what's the next input value they want me to use? Oh, you're good at your 0 times table. So, Garrett, put a 0. 2 times 0? Minus 5. So you're saying 0 goes with negative 5, or as a point, 0, comma, negative 5 is on that graph? I think it is. Spot pattern? Looks like 2 up, 1 over. Now let's do the math in the table, and let's see if it continues with that 2 up, 1 over, because that's the way we can check our answer without actually having to check our answer. Sam, what's the next input value they want me to use?
1.
So let's put a 1 in here. 2 times 1?
2.
Minus 5? 'Tis. Sam, are you saying that in a pinch you could actually just plot these points kind of in your head by just making a quick ordered list and about, yeah, okay, good. Doesn't take very long. Oh, and 1, negative 3, Mr. Dewick, put that on there. Positive 1, negative 3. Is Sam right? I sense some doubt, but is Sam right? How do you know? Fits our pattern, yes? Cool. 2. 2 times 2 is 4, minus 5. You know what? 2 goes with negative 1. 2 goes with negative 1. Okay. They left us a bit of room in case we needed extra points. And if it was a curve, I probably would try a few more. Is it a curve? Then let's just continue the pattern. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and down 2, back 1 to get that missing point down there. Am I going to connect the dots or not? Have they given me a specific situation, or is this just a generic equation? I think this is just a generic equation, which means I can assume it's continuous. I can connect the dots. Oh, yeah, C says connect the points on the grid and extend the line in both directions with arrows at both ends. Why did I put arrows on both ends? Yeah. There are more points. I'm limited to my graph paper, but I'm telling you, for what it's worth, 2 times 11,325 minus 5. The point 11,325, comma 22,645 is also on that graph. It is. So yeah, it goes forever. We did B. We did C. Oh, D. Use the graph to determine the value of y when x is 6. So when x is 6, that's right there. Oh, we're talking about that point right there. What's the value of y when x is 6? Sorry? I could also double check, Brody, by going like this. 2 times 7. Sorry, x is 6. 2 times 6 minus 5. 6 does give me a 7. Yeah, I got 2 ways. I know I'm right. Oh, we just did. So y equals 2 times 6 minus 5. They said use the equation, and you get y equals 7. I didn't even realize they were going to ask us to do that, but they did. Yeah. Says write the first value of y, write the value of y when x equals 6 in the first blank space. Oh, okay, so we can add a table here. 6, comma, what went with 6? What y value went with 6? G, so did that. G says, use the graph to determine the value of x when y equals 3. Okay, now they're giving me a y value. So when y equals 3, right here, what's the x value? You're right. Oh, it says put this information in the last row. So when x is 4, y is 3, 4, comma, 3 is a point on this graph. So complete the following statement. This relation is called a blank relation because the graph of the relation is a straight line. So here's one of your words for the day. We call this a linear. If something is a straight line, we say it's linear, which is, I think, fairly easy to remember now that you've seen the word. Turn the page. Here's our last one. Can you tell me what you think this graph is going to look like just by glancing at the equation? Oh, ooh, Brody, I'm impressed. Brody even went nerdier than I expected. I was expecting somebody to say curve. Brody said, hey, Duick, I think that's a parabola, because I remember you said all x squareds are parabolas, which I did. It's going to be a parabola. It's going to be a parabola when the vertex has been moved 6 down, and when you go up, it'll be 1, 1, 2, 4, 3, 9. You'll learn that shortcut next year. But for now, the only shortcut you have, and it still doesn't take too much time, is to do a table of values. So it wants us to try plugging in a 4 right there. So that's going to be 4 squared minus 6. When I input a 4, my out, oh, can you in your head? What is 4 squared, Jordan?
16.
Minus 6?
10.
I better get a 10. I do. Oh, I think we can do some of these in our head. So, Jordan, we're saying 4 comma 10 is on the graph. Let's do all the graphing after. Let's get the table of values first. What does 3 go with? When I input a 3, what do I get? Don't think so.
Oh, so we get 3.
I think 3, yeah? You get 9, take away 3. You know what? This is just crowded. I'm not going to write the brackets around them. You guys can. Put a 2 in. 2 squared is 4 minus 6 is negative 2. 2 comma negative 2 is a point on this graph. What does 1 go with?
Negative 5.
Negative 5. What does 0 go with? Negative 6. What does negative 1 go with? Because negative 1 squared is 1 and 1 minus 5. Negative 5. What about negative 2? Also goes with negative 2. Negative 3 goes with 3. And you know what? Let's add negative 4. What does negative 4 go with? Okay. Let's plot. 4 over, 1, 2, oh, 10 up, I can do that. 3 over, 3 up. 2 over, negative 2 down. 1 over, negative 5 down. 0 over, negative 6 down. Negative 1, negative 5. Negative 2, negative 2. By the way, do you notice this graph is symmetrical? Do you see it, Sam? You can split it right down the middle. In fact, you'll learn next year with a parabola, if you're in a rush, you can just graph half of it and then just yoink, flip the other points across. Yoink, flip the other points across, and that also works. Here is my lovely, pretty parabola. B says plot the points. Greg, we did that already, yes? C says use the symmetry of the graph or the table to predict the value of y when x equals negative 4. Now, we actually calculated it, but that was kind of a waste of time. I might have noticed from the graph it's symmetrical. If positive 4 gives me a 10, negative 4 is also going to give me a 10. So we noticed that. We could use the equation. We already wrote the values of y when x equals 4 in the table of values. We already connected the points in a smooth curve. Why do you think this is called a nonlinear relation? Yeah, the fancy word for curve is nonlinear. Any relation is either linear or nonlinear. If it's linear, in science, that turns out to be really important. If you know it's a linear relation, it means that when your independent is twice as big, your dependent is twice as big. When your independent is 3 times as big, your dependent is 3 times as big. When your independent is 4 times as big, you know how many times bigger your dependent is? 4 times. Nonlinear, there are all sorts of nonlinear relations that show up in physics. And they don't follow that 1-to-1 ratio. Is that it? What's your homework? So what's your homework? Take a look at assignment 2. I think you can try number 1. I think you can do number 2. Think you can do number 3. Skip 4. 5, A is good, B is good, C is good, D is good. Yeah, I think all of, yep, 5 is good. Ooh, 6, a nonlinear. Cool. Yeah. 7, A is good. Yeah, B is good. We may end up doing all of 7. I haven't. Ooh, yeah, sure. C is good, so all of 7. And 8 and 9, sure. So I think I just skipped 4, did I? I assigned everything but skip 4, is that right? Almost tempted to assign 4 just so for once I actually assign forget it. And the answers are attached if you get stuck. So if you're wondering what some of the graphs are supposed to look like, they are attached there. No cheating, try and figure it out yourself first. I'm giving you, holy smokes, 35 minutes. I think you can probably get all the homework done and have no homework for the weekend, which would be kind of nerdily cool.